Now we're going to look at binary heaps, which is an ingenious and very simple data structure that's going to help us implement all the priority queue operations quickly. So the idea of a binary heap is based on the idea of a complete binary tree. So a complete binary tree, well, first of all, a binary tree is either empty or it's a node with links to left and right binary trees. So that's an example of a binary tree. A complete binary tree is one that's perfectly balanced except possibly for the bottom level. So there might be a few nodes on the bottom level and one level lower than the bottom level, but otherwise all the levels are full. And we'll see how that looks in just a second. The property of a complete tree is that the height of a complete tree with n nodes is the biggest integer less than log base 2 of n. And that's really easy to convince yourself that that's true because the height, if we add nodes one at a time, going from left to right on the bottom level, say, the height only increases when n is a power of 2. Complete binary trees actually happen in nature. Here's an example of one that goes 1, 2, 3, 4 levels at least. So 16 bushes at the end there. All right, now the way we're going to use complete binary trees to implement priority queues is to, first of all, associate information with each node. We'll put our keys in the nodes. And also, we're going to represent it with an array. So when we start putting the keys in the nodes, we're going to impose one more condition that's called heap ordering. And the idea is that the parent's key is going to be no smaller than its children's key, and that's true for every node in the tree. The array representation, all we do is we start with indices at 1. It's a little less calculation that way. We leave A of 0 empty. And then we just take the nodes in level order. So first we put the root, then we put the 2 nodes on the first level going left from right, and then all the nodes on the third level going from left to right, and so forth. This is interesting because we can draw the tree to get more intuition about what's happening, but in the actual data structure representation, we don't need any links at all. It's just an array. The way that we move around the tree is by doing arithmetic on the indices. So let's look at a few properties of binary heaps. So that's complete binary trees represented in an array with keys in the nodes satisfying the heap order property. Well, the first thing is that A of 1 is the largest key. It's larger than the keys. There's 2 children and they're larger than theirs and so forth. So it's the largest key in the data structure. The other thing is, as I just mentioned, you can use the array indices to move through the tree. For example, if the node is at position k, index k in the array, then its parent is at k over 2, and that's integer divide. So the parents of, say, h and g are both n. H is at 10, g is at 11, n's at 5. So both of those are 10 over 2, 11 over 2, integer divide is 5. And going the other way, it's easy to see that the children of the node at k are 2k and 2k plus 1. So we don't need explicit links at all to represent these data structures. We can just use array indices. So that's the basic setup or the invariant that we want to maintain in this data structure. And now what we're going to do is take a look at just a couple of different scenarios that where we violate that invariant temporarily and then fix it. And that's going to give us the flexibility that we need to implement priority queue operations. So one scenario shown here is if for whatever reason a child's key becomes larger than its parent's key. So in this case we have an example where t, the node t here, its value changes and it becomes larger than its parent key p. So the heap order condition is satisfied everywhere except at this node. Well, it's easy to fix this one. All we do is exchange the key in the child with the key in the parent. After that exchange, then that would have T up here and P down here, then the heap order condition is satisfied at that node because the parent was smaller, so that one's smaller. And this other one is still smaller, so T is, after it's exchanged up here, will be bigger than both its children. But the heap condition will be violated because T is still smaller than S. So we have to do it again, exchange it with S. So we move up the tree, exchanging the larger key with its smaller parent until we get to a point where it's larger than both its children. That's restoring the heap order along a path from the place where it's violated to the root. You can think of that as kind of like the well-known Peter principle, where a node gets promoted to a level where it finally can't be better than its boss. It's a level of its maximum incompetence. And implementing that in code is really easy. We call that the swim operation. It swims up to the top. And if we have a node at index k and we know the heap condition is violated there, as long as we're not at the root and k's parent, k over 2, is less than a of k, then we just exchange it with its parent and move up. That's the swim operation to eliminate a violation when a key value increases. So, for example, this gives us a way to insert a new element into a heap. What we do is we add a new node at the end of the heap. So that's one position over. The thing is, remember, represented in array, 1, 2, 3, and so forth. So the next empty position in the array, there's a place to put a new node. And then we just declare that that's part of the heap. And that node, well, if it's less than its parent, we're fine. But in general, we have to check whether the heap condition is violated and exchange it with its parent as long as it's smaller. And that's just perform the swim operation. So if n is the number of items in the heap defined to be in the heap, we're going to increment it, store our new key there, and then perform the swim operation. So that's a quick implementation of the insert operation. And notice, since it's just going from bottom to top in the heap, it takes at most 1 plus log base 2 of n compares. Now there's another scenario where a key becomes smaller. So for whatever reason, a parent key decreases, it might become smaller than one or both of its children's. In this case, the value at position 2 is changed to h for whatever reason, and that's smaller, in this case, than both its children. So how do we fix that violation? Well, that one's also easy. We figure out which of the children is larger. In this case, it's the s, and we exchange that one with the one that's violating the condition. So that's moving the smaller key down. After that exchange, then S is in position 2, and it's bigger than both P and H, and the heap condition is only violated, again, where H is sitting. And again, we keep going until getting to the bottom or getting to a place where both children are smaller. And that's maybe a little bit what happens when a new boss is hired from the outside. And then the two subordinates struggle to take over that position, and then the boss would get demoted to its level of competence. And again, that level of flexibility, here's the implementation of it. And again, it's quite straightforward, using the index arithmetic to move around in the heap. And that's called the sync operation because we're going down in the heap. If we're at position k, then what we need to worry about is the nodes at 2k and 2k plus 1. And the first thing to check is find out which one's bigger. It's either 2k or 2k plus 1, and so set j accordingly. So that's j now, is, after this statement, is the larger of the two children. And don't forget to check that we're going off the end of the heap. And then if the k is not less than either one of those, then we're done. If it is, then we exchange with the larger of the two children and move down the heap. Again, just a few lines of code to eliminate the violation when a key value in a heap decreases. And that one we're going to use to implement delete the maximum in a heap. So delete the maximum, we have to do two things. One thing is the size of the heap has got to go down by 1. The other thing is return the maximum. Well, we know the one that we want to return is the one at the root, so we'll save that value away to return to the client. And then, since it has to go down by 1, the place to get remove the element from the heap is at the end of the array, because it's now going to have to not occupy that position. So we take that element and replace the root with it. So move the h up, and actually put the root value there, just exchange them, but it's no longer in the heap. Now, that element, which went from the bottom to the top, is most likely going to violate the heap order. It's going to be smaller than both of its children, so we do a sync. Now, in this case, to implement delete max, we save away that value at the root in max, and we eliminate loitering by nulling out that vacated position, then return the max value. So that's an implementation of the delete max operation for a heap using sync, where a key value that decreases goes down in the heap. So let's just take a look at what happens with a real heap with the demo when we do these things. And you'll have a good feeling for how this data structure works. So we're starting at some point where we have these 10 keys in a heap, and it's heap ordered. So we've drawn the data structure with the links, so we have an intuition for what's going on. But all the program sees is the array in gray at the bottom, where T's in position 1, P and R position 2 and 3, and so forth. So now suppose that we're supposed to add S. So to add it to the heap, that's going to go in the position at the end. And then now we've added it to the heap by just incrementing n and putting it in there. But now we have to bring the heap order back into condition. And so that's going to, that key is larger than its parent, so we're going to swim it up. Exchange it with its parent as long as it's smaller than its parent. So first thing, it goes up to exchange with the S. It's still bigger than P, so we exchange it with the P. And now we're done because the S is not bigger than T, and the heap order condition is now satisfied everywhere in the heap. So with just 2 exchanges, we insert that new element into the heap in this case. Now suppose the next operation is remove the maximum. So we're going to take T and we're going to exchange it with the last element, and then declare that to be no longer part of the heap. So now we have to bring the heap order back because it might be violated at the root. So now we invoke the sync, where we exchange that node with the larger of its 2 children until we find a place where it's larger than both its children. So S is the larger of the 2 children, R and S, and now H is still smaller than both its children, so we promote the larger, which is P. Now H has no right child, just a left child, and it's larger than that one, so we're finished with that operation. We've removed the maximum, and we still have our data structure heap ordered, and our n keys stored in the first n positions in the array. Let's remove the maximum again. Again, we take it out by exchanging, this time G with the root, and then decrease the size of the heap by 1, just take that out. Now the node at the root violates the heap order, so we have to exchange it with the largest of its 2 children. In this case, that's R. Again, G is not larger than its 2 children, so we have to exchange it with the larger of the 2, that's O. And now we're done, we've removed the largest again. Now suppose we insert S back into the heap. So that's adding it at the end, violates the heap order, exchange it with the parent who's smaller, and keep doing until we get to a place where it's larger than its 2 children. In this case, S goes all the way up to the root, and it's all heap ordered again. So that's a little survey of some operations on a heap, and you can see how every operation is done with just a few exchanges along the path from the bottom to the top, or the top to the bottom. Okay, here's the complete Java implementation of a priority queue using the binary heap data structure. It's actually not so different from the elementary implementations that we looked at in the last section. Our representation is an array of keys and a size. That's the number of items in the heap. For simplicity, we'll show the code where the client gives the capacity of the heap. We can use a resizing array in an industrial strength implementation, the same that we did for stacks and other data structures where we use arrays. So we'll build a new array of keys, and we have to use an ugly cast because we can't have generic arrays in Java. So it's comparable, and we need one more than the capacity to handle this thing where we don't use position 0. So the priority queue operations is the insert and del max that we just showed in the previous slides. Isent is just checking whether n is equal to 0. We have the swim and sync functions that we showed earlier, and then we have helper functions less and exchange that access the array directly so that the code doesn't have to access them directly. That's a complete implementation of priority queues in Java. And this implementation by itself is extremely significant because it's really very simple, optimal representation of the data, and only a little arithmetic